How's the pupper? Hi, you say hello? Well, today we're going to start out our testing of the UT61E Plus, doing our temperature testing. So you can see I have our meat packing box out. She seems very interested in what's going on here. Huh, aren't you? She's been with us about 8 months now. Yeah, you be good girl. Yes, oh, show him your face. Oh, yes. Oh, yes. Oh, yeah. You're a playful puppy, aren't you? Yeah. Okay. So the plan is to take this thing down to basically as cold as we can get it. Hopefully we can get down to -10. Yes, I'm right here. And then, yes. And then we'll heat it up and we'll see what the temperature drift on this looks like. And you can see we have everything buttoned up. Of course, using these Peltiers is not very efficient, so it takes a better part of the day to get this thing down to a reasonable temperature. The last time we used this setup, we were looking at the Bryman meter, and we were right in the middle of summer, so we don't have that fighting against us this time. The lab temperatures are a little cooler today. Of course, we had to reopen the box because I forgot to disable the auto power off function, but we should be good to go now. I'd forgotten that when I had ran the original UT61E, I had done that in its millivolt range, so I've gone ahead and changed this meter over to the millivolt scale, and I'm currently injecting 1 millivolt, so it's going to take a little while for this thing to stabilize again. Alright, it looks like we're pretty much at the limit of what we're going to be able to reach with the temperature. It's been sitting below 7 degrees now for quite some time. You can see it's basically gotten down to about 8.9 degrees below zero. So to give you some idea, it took me, I would say, 8 hours to run those temperature tests the other day. And that time is dictated by the smaller Peltier junctions that I have in that packing box. So here you can see I have our transient generator out. It's attached to our high voltage probe, which is going off to our oscilloscope. The oscilloscope is currently set for 500 volts per division. You can see we're 2 divisions up, or 1000 volts. And it's 50 microseconds per division. So if you go up 1 division, 2 divisions over, it's 100 microsecond full width half height. And again, the transient generator has a 2 ohm source impedance. For fun, we have our current transformer connected to the channel 2 of the oscilloscope. Of course, we just fired this with an open, so there is no current draw. So we're going to be starting off with this 1000 volts, and we'll apply 5 transients, both positive and negative, with the meter set to each function. So here we go. You can see there's very little current being drawn. Same with the resistance mode. Of course, we have engaged the low voltage clamp, but the current is just very small. If I turn this up a little bit, you can see a little bit of current. And again, we swap the 2 leads to change the polarity. You see, even in the HFE mode, it draws a little bit of current. You can see, of course, it changes the full width half height too, putting that little bit of load on there. Again, this transient generator doesn't put out a whole lot of energy. That's it. We'll go ahead and functional test the meter. Alright, the meter checks out just fine. You can see I've reprogrammed our generator for 1.5 kV. We're now 3 divisions up. Just like before, we'll be applying 5 transients. both positive and negative with the meter set to each mode. Here we go. See, the meter's drawing a little bit of current now. That's it. Alright, the meter survived that test just fine. You can see I've reprogrammed our generator. We're now 4 divisions up, or 2000 volts peak. Again, we'll start out with the positive transients. And here we go. So there's a little bit of current, but not much. Could be the MOV starting to engage. Get a little bit of current being drawn. Alright, that's it. I'll go ahead and check the meter out. So the meter is still okay. You can see I've changed our transient generator to 1000 volts per division. We are 2.5 divisions up, or 2.5 thousand volts. Again, we'll start out with the positive transients. And here we go. See, the current's a little higher since we're starting to drive the MOVs a little bit harder. See, now the current's starting to go up quite a bit. See, in the resistance mode, it's actually saturating the scope. Go ahead and change that down 1 division. Alright, that's it. And so the meter checks out just fine. You can see we're now 3 divisions up, or 3000 volts peak. This is with our 10 mega ohm resistor attached. Again, we'll be applying 5 transients, positive and negative. Starting out with the positive transients. Here we go. And you can see the current's up a little bit higher. Of course, the voltage is up a little bit higher than it was. See, the current goes up quite a bit when it's in the resistance mode. Alright, that's it. Alright, the UT61E Plus survived that test just fine. You can see I've reprogrammed our generator. We're now 4 divisions up, or 4000 volts peak. Now, early on I had tested a UT139C. Again, that's a UNI-T product. The very first 139C that I tested had arrived late. It was part of the $50 meter shootout, and by that point I was already testing at 3.7 kV, and that meter was damaged the very first time that I tested it. A lot of people were upset about that. Again, it's not like I'm going to restart the whole test for that 1 meter. That's part of the reason that I built this transient generator, is because this one is actually programmable. For the original testing, I was actually redesigning that transient generator for each test that I ran. Again, that very first 139 being damaged at 3.7 kV. I purchased a second one, and that meter survived at 4000 volts peak off of this generator. But then when I took it up to 5000 volts, I damaged it. So I think that 3.7 kV, it was probably very close to the limits of that particular meter. So it'll be interesting to see how this UT61E compares to the 139. I think if it passes this test, it's a pretty good indicator that it's at least on par with it. So again, this will be 4000 volts peak. We'll start out with the positive transients. And you can see current again is quite a bit higher. Of course, the voltage is much higher again. So we're putting a lot more current through those MOVs. And you can see in the millivolt ranges, that the current again is quite a bit higher. It's because it's engaging one of the low voltage clamps. Of course, when we go to resistance mode, you've got two different low voltage clamps that are being engaged, so the current's going to go up even higher. Let me just show you. I expect this is going to go right off of the screen. Yep. Let's go down another division. Oops. There you go. And again, I'm expecting the current to drop down now. You can see it does. And again, that's because we're only engaging a single clamp. And you can see the current is back to normal. Alright, that's it. UT61E Plus survived that test without any problems. You can see I've reprogrammed our generator. The scope is now set for 2000 volts per division. We're 2.5 divisions up, or 5000 volts peak. So this would have certainly damaged the UNI-T UT181Cs that I looked at. We'll see how this meter fares against this. Again, I want to be very clear to the UNI-T fanboys that this meter has been modified. It no longer has the original transistors and the low voltage clamps. So if this meter does indeed survive this test, that does not mean that a brand new meter from the factory would. I really have no way to know that. So again, we'll start out with the positive transients. And you can see the current's up quite a bit. You'd expect that. So, yeah, about one division. See, the current is 2 divisions up. Again, this is in the HFE mode. Yeah, I was going to show you the current. You can see it's a little over 2 divisions up. And again, that's in the resistance mode. I'm going to change it over to millivolts. And let's see how this affects it. Would expect the current to go down a little bit, which it does. And again, we're expecting the current to go even lower in the volt mode, which of course it does. Alright, that's it. And again, you can see the current profile looks normal. Let's just go ahead and switch the meter over to resistance real quick. And you can see it's still reading a open circuit. I'll go ahead and functional test it, but it looks like it's probably going to be okay. Doesn't appear like we've damaged the meter at all. You can see I've changed our generator. It's now just shy of 3 divisions up, or roughly 5.8 kV. Again, this is with our 10 mega ohm resistor. You can see it's basically reading spot on still. So this is the maximum this generator can put out, well above what the UNI-T 139Cs had survived to. Alright, here we go. You can see again the current's quite a bit higher. You can see now that one of the low voltage clamps has been engaged, how much higher the current is. Again, this is in the millivolt setting. I'm expecting that the current's going to go up higher, again being in the resistance mode. Let's just see what happens. And you can see quite a bit higher, almost another division. And again, you can see the current is back to normal. Looks like the batteries went out in the camera. It's actually only got one more transient to go. Hopefully the batteries here will make it through to the end of this. You can see current's basically back to normal. Well, that's the end of the testing. Unfortunately, I'm not sure where the batteries died at. Hopefully it was right towards the end of this. I'll have to go back and review it. Anyway, let's go ahead and just pop the leads out real quick. And have a look at the resistance mode. Again, you can see that the meter is reading an open circuit. Good sign that the meter is going to be okay. So I'll go ahead and functional test it. I had to delay this testing. Unfortunately, the battery died in the scope, so it had to be replaced. And to change the battery out in this thing, you basically have to take this completely apart. One of the problems with this is, of course, it's made out of cheap plastic, and this is cracked along the edge here. Luckily, it's not a thermoset plastic, so what I did is I had some gray plastic that I basically fused into this and built these two corners back up. All of the bosses hold this bezel in place. I think about half of those had broken, so I refused all those, and then I re-drilled them, and I went to a longer screw than what the bezel originally had in it. This is actually very sturdy now compared to what it was when I first received it. Other than that, I didn't really notice anything else going on with the scope. Of course, this has that solid state drive in it. That's now been in there for about 6 years. Still working fine. Alright, let's go on with our testing. So I've gone through a complete functional test of this meter, and there's no problems with it whatsoever. Give you an idea of the accuracy still. This is our 1 mega ohm resistor, and you can see it's still reading spot on, just like it did when it was new. Here's our 100 ohm. So I think next what I'd like to do is a simple drop test of the meter. So this is a 2-inch thick piece of hardwood sitting on the concrete floor. We'll be dropping this meter from about 1 meter up. See, it didn't shake anything loose. Appears to be fine. So for this next demonstration, what I'd like to do is use our little pocket NanoVNA. You can see it's sitting right here to measure the input impedance of these 3 different meters. So we're going to start with the UT61E. So I'd like to do this impedance measurement with each meter set to its resistance mode, because it'll enable 2 of the low voltage clamps of the meter. So that should give us the lowest impedance. So this is the basic configuration. We start off with port 1. This will tie to a DC block, and that'll go to a T, and then to another DC block, through our common mode transformer, and then to port 2. And of course, with these meters set to their resistance mode, there's going to be a voltage present on the output of that, and that's the reason to have these 2 DC blocks. We don't want that DC feeding back into our NanoVNA. And because the 2 ports are physically grounded to one another, this common mode transformer breaks that ground loop. If you're going to use the network analyzer to measure low impedances, you'll need something like this to reduce the errors at the lower frequencies. Again, this is all coaxial. So here's our 2 DC blocks, our T, and this will just go to a BNC to banana connector, and then we can plug this directly into our meters. Alright, so we're going to start out with a 50 ohm resistor. Again, we're just going to attach this directly to the T, and then we'll go ahead and start a sweep. Now we're sweeping between 20 kilohertz and 50 megahertz. And you can see it's basically 50 ohms. We're up to 200 kilohertz right now. Looks like it's starting to roll off a little bit. You can see it got up to roughly 55 ohms, but for the most part it stays fairly flat. Now, of course, these banana connectors that we're using aren't going to help our signal quality, but it should at least give us some indication of how these meters behave. Again, we're just going to place this in the resistance mode. And let's go ahead and attach our VNA. You can see the meter is reading roughly 21 mega ohms. Now again, with this particular meter, you may remember it has two PTCs in series rather than using a surge rated resistor. Now again, remember what I said is we have a whole second circuit out here that has two more PTCs, and these are in parallel. So one of these legs is the current source and the other one is the voltage monitor, and of course that's how the meter is going to read resistance. So let's go ahead and do a sweep now. You can see it's starting off at roughly 4K ohms, fairly high. And you can see as we worked our way all the way up to 50 megahertz, the impedance got all the way down to basically a dead short. So let's see how this compares against the BM869S. Again, we'll just place the meter into its resistance mode. I'll go ahead and store the data for the UT61E into memory 1, and let's go ahead and start another sweep. We can see the Bryman meter is quite a bit higher. It looks like 6.5K versus 4K on the UNI-T meter. You can see right at a megahertz the two cross over, and it looks like at about 3 or 3.5 megahertz they cross over again. And you can see what's happening now is the Bryman meter's impedance is actually increasing, and that's because of the inductance of the meter is dominating the measurement. So as we got closer to 50 megahertz, the UNI-T basically acts like a short, where our Bryman essentially is staying at a fairly high impedance. Let's go ahead and look at our BM789, and again we'll just place it in the resistance mode. So we can see the impedance on this meter is a little bit higher than the UNI-T. Again, similar to the BM869S. It looks like the two are going to cross over before a megahertz. So about 700 kilohertz it looks like they cross. And again, we can see the UNI-T now is starting to flatten out. So very similar to the BM869S. Again, it looks like it gets down to roughly 500 ohms, but then works its way back up to roughly 2K ohms. So again, why does this matter? Well, again, if you go back and look at part 1 where I was reviewing the 61E Plus, I was looking at this frequency counter where they rate this thing up to 220 megahertz. And so I had hooked this thing up to a RF generator. I couldn't get it to work, so I had hooked up a small power amplifier to increase the signal level into the meter. And I was slowly creeping up on the power, and I touched the side of the meter. Of course, the meter was hot, and we had damaged the meter. So that's why it's important. So of course you could imagine if you took a battery, say your car battery at 12 volts, and we put a dead short across that battery, of course that short's going to get hot. Now if you did the same thing and it was like a 1K ohm, for example, that resistor won't dissipate enough power where it'll even be warm to the touch. So that's what we saw in part 1. I think that power amplifier can put out to about 100 watts, so not a lot of power, but enough to reflow the solder and do a small amount of damage to the circuit board. So there is a different mode on this BM789, and that's this low Z. And of course the way that this works is it places a load across the AC line voltage, and most meters will do that with some combination of PTCs. So in some meters they'll actually use two PTCs in series. So if that's true with this particular meter, we would expect it to behave like this UNI-T meter when it's in the resistance mode. So let's just have a look. Again, we'll leave this in the low Z mode, and let's start a sweep. And again, we can see that it gets down to roughly 500 ohms, and then it starts increasing again. So let's have a look at one last meter. This is the 121GW. The reason I'd like to look at this meter again is it has the low Z mode. Now again, to be clear, this is production 2, which is the meter that I used for all my destructive testing. It's got version 202 firmware in it. So we don't really care if the meter is functional or not for this test. Again, we just want to have a look at this low impedance mode. So let's try running a sweep now. From what I remember, this meter has two PTCs in series. It's interesting, you can see the impedance is starting out a little bit lower, roughly 2.8K. But I don't remember those two PTCs being in series with anything. I think they switch right across the line. As a matter of fact, I remember that the switch contacts don't have enough clearance in this meter, and the contacts can actually break over when I transient test the meter. Looks like a race to the bottom. Just like what I thought, the two PTCs on this have no series resistance. If we were to hook this meter up in the low Z mode to that amplifier, I would imagine if we configured that the same way that we damaged the UT61E+, we would also damage this 121GW. Well, I think that's going to be it for this video. What I'd like to know is, what do you want to see done with this UT61E+ right now? I could pull out the other transient generator and we could continue to increase the levels until we damage the meter. Or the other thing I'm thinking about is we could also life cycle the switch of this meter while it's still in working order. What I'm thinking is we might learn more from the meter by doing a mechanical test like that. The problem with doing the destructive test is, again, because I've changed out the transistors, it doesn't really represent what the production meter would do. But I think from a mechanical standpoint, we haven't really altered anything in the meter. So if this thing gets ground to dust, I'm pretty certain that a production meter would do the same thing. So let me know what you think in the comments. So until the next video, stay safe and we'll see you then. Later.